Let's look at linear systems of two or more equations or inequalities. Let's think about that graphically. Anytime they intersect, that represents a real solution of the equations. Another way to say that is anytime I solve two linear equations, the intersection points are the solutions of those equations. So I've got three cases that are possible when I look at them visually or graphically. The lines could be parallel, in which case they don't intersect at all, which means there are no real solutions to that equation. I've got two distinct lines, they're parallel, and there's no intersection. So if I need to find no real solutions, I know I'm looking for a parallel line. On the other hand, I could have literally the same line. So if my second line was not distinct and it lied exactly on top of the first line, there would be infinitely many solutions, that is, real solutions. Think about it. Every point, and there are infinitely many points on the line, would be the same between the two lines. And lastly, I could have two lines that have different slopes and they intersect in one point. Two lines will intersect in exactly one point. So there's going to be one real solution in the case that my slopes are different. So these are our three scenarios and what we want to be on the lookout for in these cases. So in the parallel case, let's look at that in standard form for a second. Suppose I had 5x plus 5y equals 10. A parallel line might be something like 5x plus 5y, the same ratio of the a to b coefficients, equals 20, a different c value. They would be separate lines but parallel. That would have no real solutions. In y equals mx plus b format, that might look something like y equals, say, 3x minus 3. Or a parallel line to that would be y equals 3x. Different y-intercepts, so they're separate lines, but they have the same slope, therefore they're parallel lines. So that's what we'd be looking for as examples of no real solutions for a system of linear equations. What about the case where we have infinitely many solutions? Let's start again with that 5x plus 5y equals 10. Well, 5x plus 5y again equals 10 would answer it, but what about 2x plus 2y equals 4? Is that the same equation? The answer is yes, it is. If I multiply this by 5 halves on both sides, I would essentially end up with exactly the equation on top. Therefore, they're exactly the same, and this would be an example in standard form of infinitely many solutions. They are the same line, effectively. On the other hand, what if the slopes are different in standard form? 5x minus 5y equals 10. And I have another line that might be, say, 5x plus 5y equals 10. Or I could have 3x plus 4y equals, well, we could say 10 again. That doesn't really matter so much here. These slopes are different. The ratios of plus 5 to minus 5, the a's to b's, is different than plus 5 to plus 5. The first example is a positively sloped line. The second example is a negatively sloped line, just kind of like our picture. And of course, the point of intersection between will be the solution of two equations. Likewise, 3 and 4 is a completely different ratio altogether, thus not parallel to any of the other lines, and would also be an example of one real solution. Anytime the slopes are not the same, you must have one real solution between the lines. How do we go about solving system of equations? There are two basic methodologies: elimination and substitution. In either case, the objective is to take the two equations and two variables, eliminate one variable in your first step to end up with one equation, one variable, solve for that, and then plug that result back into the original equation, the other one, to find the value for the other variable. Let's see how that's done with elimination. In this case, I see two equations in standard form. Elimination works very well when the format of the equations are the same, and that's typically when they're in standard form, as you'll often see on the exam. So sometimes there's a real quick elimination, like in this case. I simply add the second equation to the first equation. 2x plus 4x is 6x, plus 3y plus minus 3y is essentially 0y. That cancels. And 7 plus negative 1 is 7 minus 1 is 6. So 6x equals 6. X equals 1. And I've solved for the variable x. Now I can plug that back into the original equations, one of the original equations, and solve for y. So 2 times 1 plus, substituting 1 for x, plus 3y equals 7. So I'm going to subtract the 2 times 1, or 2, from both sides. 3y equals 5. Y equals 5 thirds. My solution is x 1, y 5 thirds. This would be the point of intersection between the two lines in these equations. What about the other method, substitution? How would we go about solving by substitution? Well, substitution works effectively when the equations are in different format. Notice our top equation is in y equals mx plus b format. The second equation is in standard form. In this case, I'm not going to bother putting one into the other format to make them the same. I'm just simply going to substitute. I've already solved for one variable, y in this case, in one of the equations, and that would be the objective. If you haven't solved for the variable, solve for one variable. And then I'm going to plug that variable back into y in the second equation, which would be 2x plus 1. So when I do that, I get x plus y is really x plus 2x plus 1. By the way, when you substitute in, always put it in parentheses in case you're distributing. That way you'll always multiply it out correctly and not make a mistake. In theory, at least. So now that simply distributes to 2x plus 1 because the coefficient is 1 in the parentheses. So x plus 2x is 3x plus 1 equals negative 2. 3x equals negative 3. X equals negative 1. Now I can take that and plug back into my equation. Y, we know, equals 2 times x, which is negative 1, plus 1. That's negative 2 plus 1. Y equals negative 1. Here, the intersection point between the two lines is going to be negative 1 comma negative 1. That is our solution to that system of equations. Let's take a look at a more challenging case where the two equations don't eliminate and tidy up as quickly or easily as our first examples. Now remember, the SAT is designed for questions to be answered in about 30 seconds. So usually there is a way to tidy them up pretty quickly. But in this case there isn't. So let's go through that. I've got 5 and 3 as coefficients of x, and 4 and 9 as my coefficients of y. None of those are nice multiples of each other that I could easily sort of eliminate or work through. So I'm going to have to scale both equations. I'm going to eliminate on x's. I could do it either way, x's or y's, but I'm going to choose x's. And I'm going to multiply the 5 by 3, the coefficient of the other x. And I'm going to multiply the 3 by the 5, the alternate coefficient, which is going to give me 15x for both of them. And then I'm going to subtract one equation from the other. So effectively, I get 15x plus 3 times 4 is 12y equals minus 30 times 3 is minus 90. And in my second equation, I will get minus 15x. And minus 5 times minus 90 is plus 45y, and minus 5 times minus 18 is plus 90. So what does that work out when I add the equations together? I eliminate my x's. I get 12 plus 45 is 57y equals minus 90 plus 90 is 0, which means y equals 0. Okay? So if y equals 0, I can plug back into the other equation and say 5x plus 4 times 0 equals minus 30. 5x equals minus 30. X equals minus 6. My solution point is minus 6, comma 0. Well, that wasn't too bad for what was a slightly ugly scaled elimination method up front. Let's tackle this same system of two equations by substitution. It's a little more complicated than our previous cases because we don't have one equation solved for y or solved for a single variable. We have to do that up front. So I could take the first equation, for example, and try to solve for x. Let's say 5x plus 4y equals negative 30. So I know 5x equals minus 30 minus 4y. Divide through by 5. X equals minus 30 fifths minus 4 fifths y. And that in turn equals minus 6 minus 4 fifths y. I'm going to substitute that back into my second equation for x. So now in the second equation, 3x becomes, I will substitute minus 6 minus 4 fifths y. And I continue the rest of the equation as minus 9y equals minus 18. Now I'm going to distribute minus 18 minus 12 fifths y minus 9y equals minus 18. Right away, I can see the solution now is going to be y equals 0. The 18s or negative 18s cancel, and minus 12 fifths y minus 45 fifths y, which is a common denominator, will be minus 57 over 5y equals 0. Don't really care what that coefficient is. I didn't really need to worry about that complicated, messy math there, because ultimately I'll divide through by both sides, and the answer will simply be y equals 0. That's exactly the same result we got in our elimination example. So the two work out, and then I would plug back in and find my x value and get the same solution. So slightly messier substitution and elimination examples, but now you see in examples, you can hopefully do it yourself if you run into that complication on the exam. Sometimes on the exam, we'll see a problem that presents a system of two linear equations in standard form in this case. 10 equals ax plus by, and we're told a and b are constants or coefficients. The second equation is 5 equals 2x plus 3y. The question is not solve for x or y. Don't solve the system. The question is what values of those constants a and b, or in this case a plus b, make the equations true for all real x. There's an alternative version that it's never true for any real x or real y in this case. Well, what has to be done to make that happen? In this case, we actually need the equations to be exactly the same. So I do see a similarity in equations here. If I multiply the bottom equation by 2, I'll get my constants on the left side to be exactly the same, and that's good. I need that to happen. And on the right side, 2 times my 2x is 4x, and 2 times my 3y becomes 6y. I need the 4x plus y to match the ax plus by. I need those to be the same. Only then will the equations be the same, and no matter what x and y are as real values, the equations will hold true. So in that case, I'm really solving for the coefficients. I need the a to equal the 4, the two coefficients of x. I need the b to equal the 6. They're the two coefficients of y. So b equals 6. Well, that was pretty simple. Those are the solutions that make the two equations true and solve for the constants such that for any real x and any real y, this system is always true. And they're asking for, in this case, a plus b, so that's simply 4 plus 6. The correct answer here would be 10. Notice that's slightly different than solving for the system of equations. You can learn more about linear solve for the constant problems in the How to Solve sections for the appropriate topics on math.